now talking about data that is a mean. We're talking about a mean that somebody would get versus 10.2, which was where the data happened to be a percentage. So that's kind of the big distinction. So if the wedding cost is proposed based on the Most Holy Internet to be this expensive per wedding, then you said you disagreed with that. And so let's see, I don't know what we should say. Let's say we think that, I'm going to say no, it's less. Can't be that expensive. It's got to be cheaper than that. There's no way it's that expensive. That's insane. And so you say, no, it's less. And so then you go do your study. And in last section, it was p hat because you went and did a study. But this time your study, and we'll do this in just a second, a little bit more in detail, but let's just say the numbers have already been crunched. And so you found that in your sample mean that you took, and as I've said before, this is a sample mean as well, even though it's written as a population mean, because they did not check with every single person. There is no way. But at least that's what's proposed. So you go find evidence that sure enough, it's actually less. And so you got, I don't know, let's say $22,000 or something like that. Let's keep it simple. You found it was only $22,000. Again, our gut reaction or knee-jerk reaction to that should be, see, I was right. Because look, it's less. But the question is there evidence? Given that your study got 22,000, and we've talked about how those sample means are evenly distributed or normally distributed. So maybe you just got a particularly low one. Maybe the right answer is actually higher and it's 30,000 now. And you just happen to get a really low one because you asked kind of the wrong people, or you just randomly asked people and you just happen to get one of those low numbers. So again, the distribution of the sample means is normal, and this is just one of them, and we don't really know where it lands. So this is not enough evidence necessarily, at least mathematically, to say, yeah, see, we were right. This is wrong. They got it wrong, or maybe just time has changed. So the question is, do we have evidence? Now, remember, one of the most important pieces about this number right here is how strong is it? This is my own language, but is that a strong number? What does that mean? I'm kind of asking you to read my mind here, but what makes that number either something that's like, wow, we can count on that number, versus who cares? Yeah, the end. In other words, if you checked with 8 people, then this number is not very solid. But let's say you checked with, I don't know, 37, which also feels pretty weak. Do you agree with that? That's a pretty weak number too. That's not very big. You didn't check with very many people. And so let's see if we can find evidence. Evidence at a, I don't know, let's do something weird, 0.03. Again, my open math is going to call this a significance level. Significance level. Red is running out of ink. So is that enough evidence? So what I will probably ask you on the test. So the hypothesis. The null hypothesis here is that mean is indeed 25,631, whereas you are saying, no, I think the mean is actually less than that. The only thing really important here is just this word, because as I hope you know, that really determines what do I do with this 3% level of error that I'm kind of willing to accept. I'm willing to accept the math here, and there's maybe a 3% chance that I screw this up. So I think the easiest method, and I'm saying this because this is what I would suggest you do for the test. You don't really have that luxury on the MyOpenMath homework, but is just to get z-scores for both of those. In other words, get a z-score for what happened here, get a z-score for 3%, and see what that looks like. So in the language of your MyOpenMath, it'll ask you for a critical value. Which is really just code for what is the z-score for half of that angle or that size right there, except that in this situation, we're going to be doing it with a t-score. That's the only difference. And you may remember that these aren't terribly different if the sample size is really large. Maybe we'll look at both of them just for the fun of it. But to draw a picture of this, I'm saying there's 3% of error, and I don't have to split it up. I get to put all 3% down in, well, the left-hand tail. So all 3%, I'm drawing it way large just so we can see it. All 3% is over there. And I'm really looking for, what score, what z-score or t-score, what defines that line. And the reason this is called a critical value is because if my particular z-score that I get here falls out here in the sort of typical large area, then I'll say there isn't evidence that this study actually, allows me to conclude that I'm right, overturn the null hypothesis and say, yep, indeed, I'm right. It's less. I will be able to say that if I land out here in this tail. So it's just a question of where do I land? And so what is that t-score right there? We have done this before, but that's found with inverse t on your calculator. And again, I'm a little worried about 83 people. Does 83 have all of this stuff? This is the one that 83 didn't have, isn't it? This is the one you had to look up on the table. So given that, I will make sure this is probably not one of the options you have on your table if you have an 83. I didn't pick a very good number for 83 people. So if I say inverse t, it says, what is my area? Well, I need the area left of the tail, and that is 0.03, so I don't have to modify it. And then degrees of freedom is one less than whatever your sample size was. So since my sample size is 37, then I'd put 36 here. And you should expect a negative number for this because I'm over there. Remember the center of this is at 0. So sure enough, I get negative 1.94 approximately for that. So this is the defining line. If I'm further out in the tail, like -2, then I'll say, hey, I have evidence that the number really is wrong or has changed. If I land on this side, the right side of that, in other words, bigger than that, like -1.9, -1.8, something like that, then I will not have evidence, mathematical evidence. Don't write this down, but what if we had done this with inverse normal? Let's see, inverse normal asks for an area, and we get to leave the mean and the standard deviation alone. You notice those two numbers are pretty close to the same thing? That's because 37 is a decent size sample. But remember, the t-distribution was invented to have slightly larger tails for smaller data sets. And so they were a little safer and pushed the line further away. They pushed it out there further. So it's in a sense not a surprise that this number is a little bit less if you're conceptually understanding this. But basically, because the data is a mean, not a percent, then we're trying to use t distributions, not z distributions. Yeah, now your chart probably does not have 97% on it, just because I picked a weird number and I wasn't thinking about what you guys had on here. Yeah, so your chart has, the cool thing about the chart, for those of you who have that, is it actually lists the confidence level at the bottom. So I'd be looking at 97%. So your chart doesn't show that, it shows 95 and 98. And then it doesn't even have the right n either. So you can't get this number off the chart. I'll choose an example where you do next, maybe. Let's see. I have a copy of that chart somewhere. If I do not know where it is. So it is kind of cool to notice that, you know, the answers are fairly similar to the z-score as long as this number is fairly large. So I now kind of have a line for the location. And so then my open math, I won't use this language, but I think the other word was test statistic. So the good thing is, as I said, we're not really learning anything new here. At least you've seen this terminology before. But this is that z-score, or, well, I guess not a z-score, but a t-score. In other words, last time it was sort of a z-score, and this time we're saying, no, now we're doing a t-score. So your note sheet says that that is, well, the same as before. I take my x value, my sample mean minus the actual population mean to see how far it's below. And notice that calculation is going to be 22 minus 25. It's going to be like negative $3,000. Hey, I'm $3,000 under. I think the answer is way lower. That's what I'm going to get when I subtract that. But then I'm dividing by the sample standard deviation. Thank you. And divided by the square root of n. I want you to stay at that formula for a second. That recipe, do we have all the ingredients for that recipe? Let's see, I've got my sample mean of 22,000. I've got my population mean of 25,000. I've got n is 37. Wait, what's s? That's the standard deviation. We actually don't have that. Like that wasn't given. I want to just show you something interesting here about the data that I looked up for this, just out of interest. Notice it says on average, US couples spend $25,631, as I told you. But notice it doesn't really say anything else, all the complicated stuff we've done in this class. It doesn't list the standard deviation because maybe nobody cares. But notice it's kind of cool what it said before, or what it said after that. It said, however, the majority of couples spend somewhere between here and here. In other words, they didn't just stick with the average as though that's the only number that you would have. They actually did go one step further and say, my point is, isn't that kind of a nod to the standard deviation? In other words, you know, okay, fine, it's 25,000, but you know, what's kind of the range there? I wonder what they mean when they say the majority of couples spend between those two. What does majority mean? Is that two standard deviations thing, 95%? Is that what that means? You know, they get to define that, but in our language, that's what it would mean. So just for the fun of it, I'm going to punch numbers here for a second. First of all, I wonder if 25,000 is even right in the middle of that. Actually, I want to give you a second to think about this. Is your reasonings before I just do it? Because this actually is kind of hard. This is a thought-provoking. So if we decided to find majority as being inside two standard deviations in our language, then maybe this is their sort of little tricky way of telling us what the standard deviation is. Could you figure out what that standard deviation is if this represents the range inside which two standard deviations lives? because our recipe calls for that, right? So, and my assignment questions aren't going to be tricky like this. I would just tell you, here's the standard deviation, but this is just kind of fun to think about. That's interesting. Notice I just checked something here because I was kind of curious, is that range actually, does that range they give actually put us in the middle? So I took the top minus the mean and I got 6,408. And then I took the mean minus the bottom and I also got 6,408. So that really is in the middle. The 25,631 is really in the middle. So what I found there is the difference, right? Like how far did you go from 25,631 to jump all the way up to $32,000? It was 6,400 bucks. So if that's 2 standard deviations, then don't I just cut that in half and that's our standard deviation? That's the best guess I could make off of this. Again, I just think it's fun to add a little reality to this because this is the kind of thing that I hope you see, you know, randomly in the news or something like that and kind of go, hey, I think I understand what that's talking about. So again, I'm not going to do this on a test. I'm going to say from the start. So what is that? 3204. So from the very start, I would say this. Not going to make it near this complicated. Very start, I would have said the mean is 25 and the standard deviation is 3204. I mean, I would have said that from the start. And so now when it comes time to do kind of our problem down here, then we actually have what we need. So what is our test statistic? I take my mean of 22,000, my sample mean that is, minus the actually established most holy internet answer to this question. And then I divide by the standard deviation. Yeah, I guess you don't need that top part anymore, do you? Divided by the square root of 37, since my sample was 37. And this is going to give me kind of a z-score, a t-score. You got to be a little careful about how you type this in. Watch what I type here. So you could really screw this up and type this. 25,631 divided by 3204 divided by the square root of 37. There we go. Hopefully you see that algebraically that's not going to work. But algebra is kind of hard. Never hurts to talk about it a little bit more. So why is it wrong? Well, because that answer makes no sense. A z-score of 22,000, like that can't possibly be true. Hopefully the mistake you saw is that the top needs parentheses. If you're going to try to type it all at once, which I actually wouldn't recommend. But maybe now you think, sweet, now it's going to work. But that's actually not correct either. But that's pretty tricky. My guess is you look at that and say, why not? That's exactly what it says. And you typed in exactly what it says. Why doesn't that work? Well, the problem is your calculator knows the order of operations. And therefore, it's going to do parentheses first and get that negative $3,000. But then it's going to divide. It's just going to work from left to right. It's going to divide by 3204. But maybe you remember something from earlier math. How do you divide fractions? Because that's kind of like a whole number divided by a fraction. Whoa. Okay. How do you divide fractions? You had to go 5 divided by 2/3. That's the same as 5 times. What do you have to do to this? You math people. Decimal would work, or flip it. Now, for that reason, do you notice what actually ends up happening to the 3? It actually ends up multiplied, not divided. Now, my advice for this is just do this instead. Like you can just type exactly what it says, but in order for this to work, you got to put parentheses around the bottom too. If you did this, the answer will be right. That's actually the z-score. Very tricky, wouldn't you say? So the other thing you could do is say, okay, what's 22,000? If you don't like all the parentheses, which I kind of don't, 25,631, like you could get that answer. Hey, there's the difference. I did my study and I got an answer $3,600 less than what the internet said. And then what's on the bottom? 3204 divided by the square root of 37. Okay, cool. There's that answer. And so now I have to divide those. So if I arrow up and say that answer divided by that answer, you see that has to be the right answer, actually. I find that to be kind of tricky. Algebraically, that feels pretty painful. So yeah, so I mean, the 0.18 answer, if you just type it what it says, basically I'm going to say this. You sort of have two choices. You either figure out the top, which was negative 3631, and you figure out the bottom, which was approximately 526.7. Because that's what that giant division sign means, right? That's kind of the last in the order of operations. I got to figure out the top and figure out the bottom. Hey, look, I did that. And then when I divided those, I got negative 6.9 approximately. Oops. I hate not being able to erase. Or you're more than welcome to, I'm going to kind of type what we had to put into the calculator a second ago. But again, that's the hard part of this class is these should be algebra problems that you would have worked out taking like 3 math classes before you ever got let into this class. So that's pretty tricky, isn't it? So that's actually the right answer to this. So there's the test statistic. Where did it land? Did it land in the language of your book out here in the critical area, the place that's unlikely to land in the tiny percentage at a 3% chance of landing out there? Did it land out there? Yeah, it landed way out there, actually. It landed way out there. So our t-score landed way out there. It's in that area, our z-score, so to speak. So is there actual mathematical evidence, given that sample means are normally distributed? You take one sample, you're going to get a different answer than if you take the same sample again. By the way, this morning at the gym, put my arm into that blood pressure cuff thing, and it was super high, like you're going to die. I was just playing racquetball, so I thought, maybe it's because I was playing racquetball. But then I thought, okay, I'll turn it off, put my arm back in there. Way different. Got a totally way different answer the second time through. So it's kind of like, you know, even that machine made different measurements of me. Well, isn't that what we've been studying lately? Good for you. You got a sample mean of 22,000. But if you just go take another sample of 37, you're going to get a totally different answer to that question. So that's the importance of what we're studying right now. Just doing one sample and acting like somehow that's the truth, that is very misleading. So all of this ugly math that we're doing in response to that is to say, yeah, we know these sample means are normally distributed. So what's the chances that it would actually be past that line if we consider that they're normally distributed? And so this was way out there. Again, this is what your book would call the classic approach to this, sort of comparing z-scores. I think this is by far the easiest. So what's your conclusion? T is in, I want to say the tail. It is in that, what your book calls the critical area. In English, that would just be the tail. So we have some evidence to, and again, I don't care about this for the test, but what's the evidence? The evidence is not technically accepting the alternate hypothesis that it's 22,000. It's just rejecting the established fact. So factually, truly, technically, we do have evidence to reject the established fact that the mean is actually 25,631, which is very good news. If you're going to pay for someone's wedding, that's really good news. The answer's less.
How do you know when to use z-score versus t-score?
Yeah, and that's entirely based on your data. Is your data a percentage? That's what happened in 10.2. All of the data that people collected were percentages. And so I'm using a z-score, but if your data is, as it was here, if your data is a mean, then you're using a t-score. And I did add some language to your notes about this kind of language that I wrote into my own. So data is a percentage. Oh, okay, well then I'm using kind of this calculation using Z 10.2. I said I'm using a z-score for that because my data is a percentage. So even this formula here shows P for proportion, sample proportion. So that's why I'm using this formula. But both of these are z-scores. And as your homework assigns them, calls them test statistics. And I actually added that to the note sheet. So this z-score is calculated using a mean. And so that's kind of how I tell what's my data. Is it a percentage or is it a mean? Okay, let's try this.
So is there a difference between critical value and positive critical value?
Yeah, notice our critical value got negative 1.94, which put us over on this end because the 3% was at the bottom. Had I put the 3% at the top, second inverse t, if I'd put it at the top, then that would have been 0.97 that was to the left of it. and still 37 minus 1 degrees of freedom. Notice I get the exact same answer. It's just that it's positive, kind of saying, oh yeah, you're over on the right side.
Okay, so if it's asking for the positive critical value and we have a negative score, just drop the minus.
Yeah, and where this matters is when the test is two-tailed, which is again one of the annoying tests for this. In other words, we haven't decided which one. So let's say that 3%, let's say this wasn't left-tailed, like this one wasn't less than, we just said, hey, I don't think that's true, but I have no idea which one. Well, now because you're not committing to which side, now your 3% has got to be split between the top and the bottom, which means down on the bottom, it would be 1.5%, 0.03 divided by 2. By the way, you can even wimp out and type that in if you can't do 0.03 divided by 2 in your head, then just type that in. So the problem with this example is you don't know which tail it's in. Does that make sense? When you started the problem, you don't know which tail it's in. I don't know if it's going to be less or it's going to be more. And you don't know that until you actually do a study. As soon as you do a study and decide, and then you get an answer that's negative or less than, then you kind of know. But now that tail is much smaller than it was. Do you see how that pushed it? Where's my picture? Do you see how that pushed it way further out there? Because now it's basically .03. Oh yeah, okay, that's good. It's way further out there because it's basically based off of 1.5% now instead of 3%. So that's why I got a much number that was pushed much further out. Notice in this particular problem, had the alternate hypothesis been just that mu is not equal to this still would have been evidence because we're so much further out. We're even further out than that. But in this case, because there would be two tails, does it make sense that I don't know which z-score to give now because there's one for the bottom that we just found, but now what about the one up at the top? Let's see, 0.5%. What would that be? 0.985, is that right? 0.015, yeah, it'd be 0.985. Notice I get the same answer, just negative. So your homework assignment then will say, you know, which one to give because there's a positive and a negative. Just because the computer can't check any other way. We'll do an example like that. Now, what makes this question a little bit nice, if you will, is the fact that somebody else did the study and basically got this answer for the question. But does it make sense in the real world? You'd have to kind of do that study for yourself. You're not just going to divine up the average as 22,000. You're going to have to go actually get 37 numbers and add them all up and divide by 37. You're going to have to get your average yourself. So I want you to consider this data. So in the interest of time, I'm not going to have you weigh these yourself. Just give me 1 second here. Share screen. Which screen am I sharing? So, and this is a kind of a powerful example in the sense that, you know, product weights and so forth, but you can appreciate Snickers bars getting packaged, those little tiny thumb size ones, are getting packaged by a machine, and there's going to be variation from piece to piece to piece. Some sort of factory operations, maybe there's not any variation, but frankly, most things that people build, they are. You're all sitting at a desk right now and you're kind of, yep, every person's got the same desk, but if we broke the tape measure out, they would not all be exactly the same. There'd be a little bit of variation in it. Well, notice, and again, this is actually real data we measured in class in some previous class I taught. So this isn't just made up. This is the real thing. And notice that's not in order, but just at a glance, let's see what's the smallest one up there, 21.2. Oh, these are in order. Yeah, they're in order. So the smallest one is 21.2, but the biggest one is 24. I mean, that's quite a bit more sort of chocolate you got in grams. But if I gave you that study, then you'd have to come up with this yourself. Does that make sense? So what I'd like you to do is go into your calculator, because I'm definitely going to ask this on a test, and my open math asks this as well. But go into your calculator and enter all that data in, and you have it tell you what the sample mean and the sample standard deviation is. I'm doing this with you. I'll switch screens in just a second after I feel like I've given everybody time to type all that in. But one little side thing I'd like you to notice up here is, notice what it said right there. The package said that 1 bar weighs 17 grams. You should have some thoughts about that. It said it weighs 17 grams, and yet when I weighed them, what did I get? And I actually took the paper off to weigh these, by the way. Why do you think these are all so high if it's saying 17 grams? When they say 17 grams, what is that? What are they telling you? I want you to answer that. Like, why is that so different? Something I'd like you to leave this class understanding just an education level. It's nothing to do with this class, but it actually does in a practical sense. It's not something I'm gonna test you on. Or would say that. Come on, be brave. It's okay to be wrong. Exactly right. That's kind of related to that rope problem. In other words, that 17 grams is a promise they're making to you. Does that make sense? I mean, they're advertising that this bar weighs 17 grams. Now, if it's more than that, are you going to call and complain? I only wanted 17. No, you're going to be happy. But if your bar weighs less, then you are going to call and complain. Now, I don't know how many people measure those before they eat them, but that's actually a promise. They are having to fulfill that promise. So I'm sure in their factory, they're making sure their mean and their standard deviation. I wonder, for instance, just like the last, we won't take the time to do this, but I will give you extra credit if you investigate this. But I wonder, you know, if I took that really small sample there, I guess it's about 18 numbers, right? I wonder if the mean minus, say, 3 standard deviations or something like that is where they got that 17. I don't know, but that's actually important from a manufacturing perspective. If you take a measurement of stuff that's on every package of food that you buy, they are going to have to under promise and over deliver because they're making a promise of 17 grams. That's why it's not the average. Most of you, I would think, would have not have questioned it. What is the average on your calculator? Is it like 22 or 23, 22.5, something like that? We'll look in a second. But you might have thought that's what they would put on there. But they could say that. They could say the average is 25 or something like that. But that's not what they can do. They've actually got to promise something and then deliver on the promise. Even though this isn't like a rope that's going to kill people, still, even in this context, they've got to deliver on what it is they're promising. So you shouldn't be surprised, having taken this class, that these numbers are all higher. Okay. So let's see. I typed mine in really fast, just like you did, but I would want you to have, I'd want you to feel pretty good about this now. And of course, it's way easier to do this in Excel, right? Like type all the numbers in Excel than it is to do it in your calculator. It's way more useful. But if I go to stat, over to calculate, and one variable statistics, fortunately mine says list one, and that's where I put all my data. Is this what you got? Because I didn't check my work, so I might have typed one in wrong. There's like 18 of them. Did you get the same thing? Some people are nodding, so okay, good. So notice the sample mean, we'll call it 22.5, I guess. You could round that however you wanted. So N was 18. And the sample mean was 22.5. Yeah, maybe I'll call it 5.3. And so this is just like the last problem, except for we produced those numbers ourselves. We actually went and did the study and got those two answers. So some of you are logged in, like go online and see if you can get an internet answer for the average weight of a Snickers bar. It won't surprise me if you don't, but it's got to be fun size, or I'm going to ask Siri. Siri, what's the weight of a fun size Snickers bar?
1.6.
Yeah, I see Siri said 1.2, but it said ounces, right? Because it's speaking to us, whereas that was in grams.
Mine says 20 grams.
20 grams? Okay, let's go with that. Now, again, that's a question of what does it actually weigh? The promise on the package said 17, but the average weight is 20 according to the internet. This is kind of interesting, but notice, as I said before, we need some kind of a standard deviation. We could sort of steal one from this, but let's just make one up. We're probably not going to online find the standard deviation for that 20 gram number. So I'm just going to make one up. And notice, of course, don't we, if you will, have some evidence here that the answer is higher than that? And this is the part about the two-tailed thing I think is dumb. In other words, if I looked online and it said 20 grams, I'm not just going to say I disagree for no reason. That's what two-tailed tests really are. As I said, I'm not going to ask you a two-tailed question on the test because it makes it unnecessarily complicated. Even if you said, hey, I don't think this is true, and then I went and did my measurement of 18 candy bars and got 22, wouldn't my, maybe I should throw grams in there. Wouldn't my conclusion be, I think it's bigger. Look, that's quite a bit bigger, isn't it? Now, is this bigger? Well, it depends on what the standard deviation is. You should have a pretty good feel for that. If the standard deviation is really tiny, then maybe this is a pretty significant number. But if the standard deviation is really small, then maybe not. I'm going to make one up in the interest of time and say the standard deviation is, let's just keep it simple and say 1 gram. I'm gonna make one that shows up on your table this time. So let's see if we can find evidence at the 2%, at alpha is 2%. Let's see if there's evidence at the 2% significance level that indeed, as this would indicate, it's higher. I'd like to give you a second to give this a shot rather than just immediately do it. Is this proof mathematically, given that samples vary? If I did a different sample of 18 candy bars, then I'm not going to get 22.53 again. Given that sample means are normally distributed, did I just happen to get a high one? And so there's a chance that it actually would be down as low as 20, and so I don't have evidence. I'm gonna see if I have a copy of that chart somewhere. There's print. Talk with your neighbor, compare your answer to theirs, steal from their big brain. So the Most Holy Internet says the answer is 20. We did our little study and we think, no, I think it's actually more than 20. And our study, of course, would hint at that because we got a bigger answer. The important part about writing this down is only that you would conclude that this thing is right-tailed, meaning all 2% get to go in that right tail. And so you've got two things to compare. You got to come up with the drawing, if you will. What does this look like if I all 2% is in that upper tail? The critical value, again, is what is that score right there? So that we have a value to decide which side of that is our study on. So let's do the calculator version first, and then I just went and printed a copy of that table for you math, or for you 83 people. So remember, for your sheet, the right side's a little rougher. What do I do to get that value? Well, because my data here is a mean, not a percent, I'm using a t distribution. And notice I have a pretty small sample this time, a lot smaller than last time, only 18. So inverse t. Now, you got two choices here. One of them is you could put in 0.02 and 18 minus 1, 17 degrees of freedom. But if you do that, you're actually going to get the negative z-score. You should be saying 0.98 because that's the area left of this. But notice that when you do that, you get the same exact answer. It's just positive. But the right answer to this is the positive one. Does that make sense? Because it's the one that's over on the right side, not the one that's on the left side. But the numbers are actually the same. So I don't know, it's probably not going to be this close, but notice that's 2.22. I'll call it 2.22. So that's my critical value, 2.22, which I found by going inverse t of 0.98 and 17 degrees of freedom. Let's see. Can we get the same thing from this chart? Even if you have the calculator, take a second look at this. This is kind of interesting. This is the way this was done for years and years and years and years and years and years until calculators like this were invented. But it's just kind of cool to stare at. So down here it says confidence level. So 98% actually shows on here. And this is a little unclear. It's kind of hard to read, but notice up on top of the same exact line, it says one-tailed test right here, 0.01 if it's one-tailed. Let's see, is that true? Should be 0.02 if it's one-tailed. Now maybe I lied and this doesn't even fit on there. Because the confidence level was actually splitting it in half. But I wasn't splitting it in half because it's all up on that tail. So actually, I think I screwed up and didn't make up an example that shows up on this chart. One tail, 0.02. Well, here's pretty close. One tail, right here, it says 0.025. And by the way, for those of you that have 83s, on the test for this, if there's a prop, I'm going to check on the chart and sort of make sure this isn't the problem. But this isn't really fair because, you know, the calculator people can just kind of cheat and get the answer. That's not something I want you to miss because of something stupid like this chart. But notice where I'm looking. So it's one tail, it's 0.025. That's the best I can do. And then over here is degrees of freedom. So I'm going all the way down to 17. So I'm looking at where do these two run into each other. Looks like 2.11. That's about what we got, right? We got 2.22, didn't we? Just interesting. Your book would call this, if you happen to read that, the classical approach, which is to not compare z-scores, but to compare t-scores. So that score we got right there is really the T of alpha score, the T score for 0.02. Okay, well, what's the other score we need then? This is what your internet is calling the test statistic, which is code for, look that up on your formula sheet. What's the test statistic? It's that T0, not Z0, is equal to the difference between the sample. I'm not going to write the formula this time. I'm just going to put the numbers into it. The sample mean minus the actual proposed population mean divided by the standard deviation, which is 1, divided by the square root of n, not n minus 1. So I'm going to take the, I don't know, less algebraic approach here and say, okay, 22.53 minus 20 would be 2.53. And on the bottom, I see that I have 1 divided by the square root of 18, which is 0.236. But rather than retype those, isn't it kind of better to just say 2.53 divided by and then say answer? Like even though I wrote 0.236. Wow. And because I'm kind of making these up at random and so forth, notice that's a really high z-score. That is crazy high. Surprisingly high. So there's kind of my T0 number and there's my T alpha number. So again, the question is that in the tail or is it not in the tail? Well, this is the dividing line. That's why this is called critical. That's the key. Now I know which side my number's on. Oh, it's way over here. It's not even close. It's way over there. T0 is way over there. So, as was the case last time, my conclusion, thank you. My conclusion is I can reject the initial hypothesis. Now, I hope you see this as a little bit practical. The only thing I made up here that I don't know the answer to was 1 gram standard deviation. Interestingly, in our study that we did, because I totally made that up without thinking at all. But in our study, what was the standard deviation? Notice it said it was like 0.76. Now that was a small study, I only did 18 candy bars, but that actually at least lends some credence to that number, like 1 is at least reasonable, right? I just made it up from nowhere. So in a sense, our little study kind of says we have pretty good evidence the internet's wrong there because we literally measured candy bars. And again, this is the kind of thing that could be your final project. You know, go get some data from somewhere and analyze it. I want this to start seeming practical to you now, seeming like, hey, I could actually do this. I could actually analyze this stuff. You're more than welcome to steal any ideas of things that we've just played around in class if you just find that interesting. Or maybe you just think it's a little interesting, haven't thought about it enough yet, that seems kind of simple, I'll do that.
I'm so confused on how you came up with the conclusion. How did you find out if you reject it or?
basically, if that t-score, the t0 put us in the tail. That's really kind of the key. In other words, if this is the places you could land, like our t-score that we got down here could land anywhere in here. Basically, to land way out there, that would be unusual to land there unless we actually are on to something. There's a 2% chance basically that you would land there just randomly. In other words, the right answer to the question is really 20. You did your study and you landed way over there. There's a 2% chance that would happen just randomly. So the idea is I'm willing to accept 2% chance of error. So I could actually land over there. So this actually doesn't, in your book talks about this, but I'm not going to talk about it. But does it make sense we actually could be wrong here? I have mathematical evidence to be able to reject that 20 grams is actually the right answer in favor of the answers higher, but there's still a 2% chance I'd be wrong, but there's a 98% chance I'd be right. And so that feels like statistically significant evidence. So it's really just a question of, did you land in the tail or did you land in the kind of the main area? Did you land in the 2%? It's pretty unlikely to land out there. So therefore, I think that's evidence. If I land here, then I don't have evidence. Now, just a couple of side, like that's what I think you should, those two problems, I did them exactly the same. I did them both by comparing t-scores because I think that's the easiest way to think about it. But I will at least comment on the bottom. I will at least kind of comment down here on a couple of things. Because some of you might disagree and say, no, I actually think this is easier, but maybe more importantly, you're stuck doing this on MyOpenMath. What about the other method, not the classical approach, but the p-value approach? Let's look at it with the same exact problem. And it actually does introduce something that we haven't looked at before. The p-value approach is where you never calculate this. You take your t0 and you turn it into a percent, and then you compare it with the 2%. So p-value approach, you say, hey, I already know that alpha is 0.02. And then I'm just saying, okay, well, what's the probability that you would land out this far? What's the probability I'm going to land out that far? If I get a number smaller than 0.02, then I'm going to reject. I'm going to do the same thing. If I get a tiny percentage, if I get a percent bigger than this, remember what this was is the probability that you get. Well, in the last section, it was for p hat, but in this section, it's x bar. If that probability is less than alpha, then you actually have evidence to reject the established fact. So some of your homework, all of your homework questions will ask for the test statistic, but then some of them will say, okay, now tell me the critical value, and then compare those two z-scores, t-scores in this case. Some of them will not give the critical value. They'll ask for the test statistic and then for the p-value of that test statistic. In other words, what's the p-value for that 10.7? What am I doing? Cross it out. What's the p-value for that 10.7? Probability, in other words. What's the chance of landing out that far? Now, if this was a percent problem, I'm going to cross this out, so don't write this down. But we would use the button we've been using, normal, CDF. We would say lower limit which is 10.7, because remember, we're talking about landing way out in the tail or higher. And then we would have said the mean is 20. And the standard deviation is 1, but modified by the square root of 18. That's what we would have done. That's what we did in the last section. What are we going to do in this section, though? We're going to use a t. Cumulative, let's see, I'm going to see how this reads in your calculator. Yeah, it's exactly the same. Not normal CDF, but T CDF. Let's see what it's asking for. What is the ingredients for this? So starting from scratch. Second distribution. Again, one of my questions here is, my guess is 83 people don't have that button.
Yeah, I have it.
Oh, good. That's good, because if you don't have that, then we got to look at a table again, and that's not so good. Notice there's PDF and CDF. I need the CDF because it's cumulative. I don't want to know the probability of just getting 10.7. I want to know 10.7 plus everything above it. And so it asks the same questions. It asks, what's your lower limit? 10.7. What's your upper limit? 9,000, 9,999, whatever. And then it only asks for degrees of freedom. Since my sample size was 18, my degree of freedom is 17. And notice 10.7 is a really huge z-score, right? Because remember, that's really what it is. It's kind of like a z-score. It's way the heck out there. We're going to get a really tiny percentage for this. Probably it'll have one of those e's in it because it's going to be so tiny. Yeah. So lower limit 10.7, upper limit some big number 17 for degrees of freedom, and that spit out the answer basically 0.0, 2, 3, 4, 5, 6, 7, 8 zeros and then a 3. Since it's 2, 8, that'd be rounded to a 3. So it's a teeny percentage. You're getting a really small z-score out there. So maybe I'll even call that 0 plus. Pretty much 0. Is 0 less than 0.02? So same conclusion as before. I just think that's weirder. That doesn't feel as good to me, but that might feel better to you. Turn that thing into a percent and then just check and see if that's smaller than alpha. Now, for the sake of your sort of dumb assignment, this final note, like a My Open Math note. So this, everything we did here was what I'd consider to be stuff that makes sense. But what if it was a two-tailed test? This is the same problem we had in the previous section. If it was two-tailed and you took this p-value approach and they asked you for that p-value right there, does it make sense that what I'm doing is, in my case, I'm comparing my p-value to 0.02. But if it's two-tailed, does it make sense that you are having to cut this in half? In other words, would I be comparing my value to 0.01 then? Yeah, that's what you'd be doing because it's two-tailed. So you can't put all 2% in the same tail because you don't know where it goes. logically, you'd be comparing this to 0.01. But the other option, which appears to be what they did in my open math, if it's two-tailed and they ask you for this p-value, the other option would be to double this number, in which case then you could just compare it to 0.02. Oh, this makes me mad. So conceptually confusing. As I said before, this entire sort of term, if we were having to put 98% as a confidence level, as a confidence interval, then we split the 2% error and put it half top and half bottom. So I think it makes way more sense logically to compare 0 plus to half of that. That makes logical sense. That's something we've done a whole bunch of times. And yet my open math, instead of just letting you cut this in half to make your comparison, just kind of do it in your head. Instead of doing that, they're thinking you would just leave this alone and then double the p-value number. Then you could compare it to 0.02. So again, if you have problems with rounding, you can ask me about that and certainly send me an email and I'll fix your score. But what I'd like to do now is just shut up and let you wade into 10.3. You may also notice that there's like 4 or 5 questions in 10.3. There's not very many of them. It'd be my hope, honestly, that you get done before you even left here, only for your sake, because we're getting close to the end of this class. And I will also say, just from on a larger perspective, because I'm kind of done teaching you this material now. This hypothesis testing stuff is something you can afford to forget, unless if you're gonna go on and take more stats or something, then great. But most of you would, I think, benefit a lot from being able to find a confidence interval. That's kind of cool to be able to figure out. But this whole test stuff, like you're gonna have to be really into statistics to start questioning things in the world and so forth. You can appreciate this is pretty far down the road. If you take the class after this, Math 244. This concept is the first thing they start out with and kind of reteach this and go on from there. So I'm going to very much de-emphasize this on the last test. I'm going to put some really like one simple question, but probably not even 2 of them, and err on the side of more confidence interval type of questions, just so that you know, which I think is kind of nice. So the rest of the time is yours. Take a break if you want, but my advice would be log into my open math and make a little progress and let me help you. Yeah, so you agree this is p-tail. So therefore you have to take that 0.1 significance level, 10% significance, and you're going to split it. Come up with your answer. You split it when you look it up in the T inverse. Yeah, so they don't care if it's positive or negative because it's split, we don't know if it's negative or positive. Since your test is taken, this is so the question is, where did your test fall? Did it fall in the tail, or did it fall out?
Your answer is not right, and of course, it wouldn't be right. But if you drew a picture of the critical value, given that this number, where are you? Are you beyond that? Exactly. So, what does that mean? In English, what this language is, does this mean you can reject? The non-hypothesis? Yeah. No, so it's really like, see, the two that say there's not sufficient evidence, those are the ones you can honestly mediate and debate more. Because you do have evidence, because you're out there, right? So it's either the first or the third. That first question is just, that first answer is.
Yeah, I hear now.
But the other one's the same thing. Roll half the variables. But you need inverse to have the Z-score, the T-score.
But how can I tested this here?
Yep, yes, this is it.
Sorry,
Yep.
okay. So is this my roller?
Original study trial.
I don't give it back.
85.5 establishments, and you've got a number that's small. Well, they're both the same number, and you're sort of looking for that. You're looking for consensus scale. Your sample is low. Then in order to land.
Because we need at least 30 minutes, right?
I promised myself I would start.
If you're trying to determine that .8, that negative .871.
I know, that's why I felt like I have to at least get from 1 night.
This is the picture that contains that. And, now you come down to. You're saying, look at the pool.
I'm trying to focus on this, so it's like I took it real. When I tried to-
Yeah, good. I guess I can do this.
Interested in comparing the size of this scale to the size of this scale. That's why I think this highlight. So this is actually my number. But I landed way over here. Way over here. So it's all landed this number, see that half. That is for this number, over that number, which is the same. So,
Double that. Double this. This will not be able to.
I'm just gonna say we have a-
$2 greater. Right?
It's rejecting the notice.
I don't have that. I don't have it. Yes. Perfect. Thank you.
Questions? And so the X is the number is that 1150. Because that's kind of the number. Now you actually need to.
Yeah, and I always thought it was going to be a refund.
I went in there and changed the views and numbers. I don't know what I changed them to. So the one thing that's modified about this is.
Are you serious?
What I was actually asking this question is not go over here to this list. and look and see what happened here. I was actually looking for you to find if there's something like. So it's not, this is kind of. It wasn't really interested in this over here, so it's just this one, what's that? So this question is really. So the important thing about that command is it only works area to the left. So this one said under 1150, so that's going to answer it correctly, but this one says more than 13. So you gotta think a little more about that one. Yeah, it's actually kind of a long answer. It's asking you to help too. Okay. Yeah, if the data in 3.2, the data is a percentage, and so we have one set of formulas for that, and those are normal distribution. Norm inverse and norm. 10.3, the data is actually an average. It's very confusing, isn't it? Don't you think that's confusing? Totally confusing. The reason, when you use 0, 1 is when you're just talking about a t-score or a z-score. Like the z-score that comes from, because that z-score is cleansed, but it's mean instead of deviation. Mean is the for a z-score, for a number. It's mean. Taking this number and modifying it to a percentage. It's includes the actual. Well, if it's less than, then you get to a percent. You can reject the emotion. That puts it in the tail. You get a smaller answer. If this is the standard, you get a number smaller than that, it means you have a tail or a proof or and then you can reject. Get that answer. Let's look at it. Here, there.